Okay, YouTube, in this video we're going to extend our exploration of exponential growth and decay models to explore what we refer to as compounding interest. And usually we refer to compound interest in terms of investments, okay? And so what we'll do here is we'll kind of take a look at what this has to say and then tie that into exponential growth and decay models. So this says here that compound interest is interest paid on an initial investment. And we're going to refer to this initial investment as the principal amount here. And so we'd say that this is our initial amount, okay, is how I want to refer to it. But in terms of an investment, it's our initial investment. We say that interest paid on an initial investment, called the principal, and on previously earned interest, this is what we refer to as compound interest. So basically, you earn interest on what you have invested every year, and that goes into your total amount. But then next year you earn interest on that plus the total amount you earned last year. So now you've earned more. And basically, the more you earn more interest and put it onto the total amount that you began with, then your interest kind of gets bigger and bigger and bigger every year, and so it grows faster and faster and faster, usually on an exponential model. So we would say that because it's an exponential growth model, we could actually use our exponential growth model, which, as you recall, we'd see that our exponential functions in general are these functions y equals a times b to the x. But we'd say if we're talking about an exponential growth model, then we were saying that it's some initial amount a times 1 plus r to the t. And I'm only focusing on growth right here. I could have done 1 minus r, would have been decay, but we're saying that this is our growth model right here. And so because we are talking about compounding interest in growth models, what we're going to do is we're just going to use this model right here. So what I want to say though is that basically interest on accounts, the thing that's different about that is it's just not just paid only one time per year. And so because that's the case, we have to modify this model just a little bit, because sometimes interest is compounded every month or every week or every day or every second or maybe every 6 months. So we say that the exponential growth model y equals a, which is our initial amount or our principal amount, we're going to call this now, times 1 plus r to the t must be modified for compound interest problems. And so you're going to see this equation right here, this model right here. That's our compound interest model. And we say that considering an initial principal P deposited in an account that pays interest at an annual rate of R expressed as a decimal, compounded n times per year, we say that the amount A in the account after T years is given by all this. So man, basically alphabet soup, right? What I'd like to point out is that essentially that this P right here, let's go ahead and just write our models side by side. We would say that a growth model would look like this right here, A times 1 plus R to the t. So in terms of similarities, we're still going to see that t is time, okay? And that this a value here, we're going to write capital A. This is our amount at a given time. This is our f of x value there. So at a given time, we can tell you the amount in this account. Now with respect to p, we're going to refer to p as the principal amount. But this is really the same thing that we were using in our growth or decay models. We said this is what we were starting with to begin with. So this initial amount here, A, really is our principal amount here. And then really we see that R is the same as it was previously. We say the rate of increase, okay, or decrease each year. And in this case, we're going to say increase in terms of compounding interest. Fingers crossed, your stuff is going up. So the only other thing that we need to mention here is this in n. And I've run out of space, but n is the number, and this is really important, of times per year our funds compound. So that is to say, and we're going to write a little note about here, n values. If we have some things that compound, say annually, that would mean it only happens once a year. So when we talk about things annually, we're really saying then n would be one time a year. But what if we were to discuss something that is semi-annual in nature? That is to say that every 6 months our interest comes back to us here. Then all of a sudden we would see that this happens twice in 1 year, so our n value would be 2. Something that is monthly, okay, just to be clear, monthly would have an n value of 12 because 12 times a year is when it compounds. We could say bi-monthly. So bi-monthly would be every 2 months. So how many times a year? Well, this would be 6 times a year. And then one that I want to mention here is this biannually. And so this is 6. Biannually, interestingly, means every 2 years. And so biannual investments here compound only a half a time each year, because in a total of 2 years it will have compounded once. And so these are examples of different end values here. Basically what I'd like to show you is that these are very, very easy problems to consider and evaluate on a calculator if you know all these initial values. So let's assume a couple of problems here. We'll start with this one. It says you deposit $9,000 into an account that pays 1.46% annual interest. It asks us to find the balance after 3 years when the interest is compounded quarterly. So let's go ahead and underline a few things here. First things first, we say our p-value, our initial investment, is $9,000, and our rate here is 1.46%. So one thing I'm going to do with the rate here is we're going to move that decimal back twice, and we're going to call this 0.146 is our rate. So I'll put a box around these right here. Now in terms of our model, we do have a lot of what we need to write this model, but what we're doing is being asked to find the balance after 3 years when the interest is compounded quarterly. So in terms of time, we've actually already been told the time as well, and we're compounding quarterly, so the value of n here, quarterly, suppose we could add quarterly over here, that means 4 times a year essentially. And so we say quarterly, we say n is equal to 4 here. And so what we want to do is find the balance after 3 years. Well, to find the balance, that's kind of like saying, let's go ahead and find the overall amount here. So to use our formula, A is equal to what we started with times 1 plus. Now, this is a little bit different here. We see that we have an R over N, and instead of the power of T, we have to the N times T. And so this is just going to be a substitution game, but we just want to be really careful how we craft this expression. So with respect to our principal, we were already told that it was $9,000 here. And in terms of what we're going to write in here, we say, well, our rate we would want to write as a percentage. So 0.0146, all over n, and n is 4. Now this is all to the n, so 4 times t, which time in this case is 3 years here. We get this humongous expression right here. And so what I'd like to do is just recommend caution in entering this into a calculator. As a matter of fact, we'll just go ahead and work with order of operations. We're going to say that we'll evaluate what's inside the parentheses first here. So in terms of how to evaluate something like this, let me go ahead and turn my calculator back on here. We'll go back out to our home screen. Essentially what we could do is we could say, well, in terms of the parentheses here, we have 1 plus, in parentheses, 0.0146 divided by 4. And essentially what it's going to do is it's going to do this division first and then add it to this right here, but we'd say that this is truly what's inside of our parentheses right here. So technically we have 1.00365. Now I'm going to say that 1.00365, this is now all to the 12th power. Most times we're not going to be able to rewrite this right here, but I would rewrite out as much of it as you can reasonably. Here I went out 5 decimal places, but leave what you got up on your calculator, because technically sometimes it'll go on for a long time. But in terms of what we're going to see here next, do we do our multiplication by 9,000 first and then raise it to the power of 12? Or should we take this to the 12 and then take it times 9,000? Well, order of operations would say that we want to take this now, take our answer here, to the power of 12, which gives us this ginormously long number here. And we're going to take that answer times 9,000. So doing this piecemeal, but basically what you're going to see is that we get 9402.21. And because we're talking about an amount of money or an investment amount, I'm going to stop at the nearest hundredth and the nearest penny. So 9402.21. So we say the amount is 9402.21, and we want to make sure that we label this here, but we'd say in dollars. So we would say that looking at the big idea, the idea was that we started with $9,000, and over the course of 3 years, if our investment goes up by 1.46% every 3 months for 3 years, then by the time we get to the end of 3 years, we will have made $402.21. So what I'd like for you to try now is this one on your own, just a little bit different situation. Work this out and then hit play when you're ready to see my solution here. So we see that our initial investment here, given as $10,000, we're just going to go ahead and write down the values of all of these things for which we know values for. And so we would say that these are these values in our model here. We could say that the amount is equal to the principal times 1 plus the rate over n times per year to the nt power. But essentially what we're going to get here is that our rate, it says that we have a $10,000 gift in an index fund that earns on average 6.74%. Yikes, that's pretty good. So we would say that this 0.0674 is our decimal. Our time now, it says find the balance of your account after 10 years when the interest is compounded semi-annually, but also monthly. So what we're going to see is a couple of different situations here. We're going to say this is our semi-annual situation, and then we're going to do a monthly situation over here. So in terms of our semi-annual over 10 years, we know our time is 10 years, and our semi-annual would mean twice a year. So we would say 2 times a year, we want to go find the amount here. And so our amount, let's go ahead and write this out. We would say starting with $10,000, 1 plus 0.0674 over 2 to the n times t, where our n is 2, times t, which is 10 years here. So now working all of this out, I'm going to do a lot of calculator work here, but basically, essentially what we would start with is in the parentheses here, let's take our 1 plus 0.0674 divided by our 2 here. So what this is going to do is give us our inner quantity. Now what we want to do is we want to raise this to the power of 2 times 10, which I know is to the power of 20. And then we're going to take that amount now times the 10,000 we had out front. Taking this times 10,000, we get this 19403.96. 19403.96. And we would say that this is approximately how many dollars we would have after 10 years if it compounds semi-annually. Now looking at this as a monthly thing, and I'm going to write this over here, it would have been different. And the reason why is because our n would have been different. So we still would have started with $10,000 as our initial amount. We still would have had a rate of 6.74%, but this would have been monthly, which would have made this 12. And it also would have inflated our exponent to be 12 times 10 up here. So again, we'll dig out a value here, but looking at this on a calculator, let's go ahead and start with our inner quantity. We would say that our 1 plus our growth rate, 0.0674, we'll divide that by 12. We would have an inner quantity or an inner value of this, and now we're raising this to the power of 12 times 10. Now I would write that as 120. Do your multiplication first. But taking this to the power of 120, we get this really long decimal here, and multiplying this by 10,000. We end up with 19583.73. 19583.73. And we do want to label this here. And so what you'll notice is the more times this compounds per year, so twice a year versus 12 times a year, you see that you made more money. And I don't want to say a little amount of money, because to me, like, that's like $180 right there. I would take that. I'm just saying. But the more times it compounds, the more money you stand to make. Cheers.